Bismillahirrahmanirrahim. Assalamu alaikum, students. In the last lecture, we discussed the idea of geometric series, and using that, we tried to understand the infinite series. We discussed the definition of the sum of a series, and we talked about convergence, and we give certain examples. One example was related to bouncing ball example, and we saw that involved an infinite series which was geometric series. Let us continue and discuss today's topic. So let me write today's topic: definitions and notation. So let us discuss the idea. There are many other infinite series besides geometric series. For example, one square plus two square plus three square plus four square plus, let me name this as 1, then 1/2 plus 2/2 square plus 3/2 cube plus 4/2 raised to the power 4 plus so on. Let me name this second. And one more example, x minus x square over 2 plus x cube over 3 minus x4 over 4 plus so on. 1 square plus 2 square plus 3 square plus 4 square, 1/2 plus 2/2 square plus 3/2 cube plus 4/2 raised to the power 4, x minus x square over 2 plus x cube over 3 minus x4 over 4. You can see these are examples of infinite series besides geometric series. So we can have infinite series beside the geometric series, and 1, 2, and 3 are the examples. So in general, let me use the next page. In general, an infinite series means an expression of the form A1 plus A2 plus A3 plus A4 plus so on plus AN plus so on, where the ANs, one for each positive integer n, are numbers or functions given by some formula or rule, right? So an infinite series means an expression of this form. Let me encircle it. And name it as 4, right? Where ANs, you have AN for each positive integer n. These ANs are numbers, they can be numbers, or they can be functions given by some formula or rule. As you can see in 1 and 2, these ANs are numbers, and in third, these ANs are functions of x, right? The 3 dots in each case, these 3 dots here, these 3 dots here, these 3 dots mean that the series never ends. The terms continue according to the law of formation, right? Now, if there is apt to be doubt about how the terms are formed, a general or nth term is written as let me use another color here, 1 square plus 2 square plus 3 square plus so on plus n square plus so on. Let me name it 5. Similarly, you can write x minus x square plus x cube by 2 plus so on plus minus 1 raised by n minus 1 x raised by n over n minus 1 factorial plus dot dot dot. Let me name it 6, right? So if we have some doubt about how the terms are formed, we write a general or nth term as we have written for 5 and 6. In 5, the nth term is n square. So if you know the nth term, you can find any term by putting the values of n. When n is 1, the first term is 1 square. The second term, when n is 2, that's 2 square, and same is true for every term. So we can obtain every term from nth term. In the case of series 6, the nth term is minus 1 raised by n minus 1 x raised by n over n minus 1 factorial. Now the quantity n factorial means for integral n, the product of all integers from 1 to n. For example, you know these things, still I am refreshing your ideas. 5 factorial means 5 into 4 into 3 into 2 into 1. So it is the first product of first 5 natural numbers. 5 times 4 times 3 times 2 times 1, which is 120, right? The quantity 0 factorial is defined to be 1. We encircle it. 0 factorial is equal to 1. So using this idea, in case of series represented by 6, from the nth term, you can construct all the terms in the series, right? So you can see in 5, it is easy to see without the general term that each term is just the square of the number of the term, that is n square. However, in 6, if the formula for the general term were missing, which is this, we could probably make several reasonable guesses for the next term. To be sure of the law of formation, we must either know a good many more terms or have the formula for the general term, right? Now we can also write series in a shorter abbreviated form using a summation sign. This is our summation sign. So we can use it to write series in a shorter form. So what we do, for example, this fifth series 5 would be written as 1 square plus 2 square plus 3 square plus 4 square plus so on. We can write it, and let me use this color here. We can write it summation sigma n is equal to 1 to infinity n square. One square plus 2 square plus 3 square. The nth term is n square. So this 5 can be written in a shorter notation using this summation convention as summation n is equal to 1 to infinity n square, right? So let me name it 7. This is read as summation of n square. This symbol is read as summation of n square from n equal to 1 to infinity, right? Similarly, let me use another color here. The series 6, similarly, the series 6 would be written that is this series 6th would be written as x minus x square plus x cubed by 2 minus x raised to 4 by 6 plus so on. We write this in shorter form as summation n is equal to 1 to infinity. Then we write the nth term, which is minus 1 raised by n minus 1 x raised by n over n minus 1 factorial. Let me encircle it. You can see this series 6 where nth term is minus 1 raised by n minus 1 x raised by n over n minus 1 factorial. In shorter form, we can write it this way. Let me name it 8. X minus x square plus x cubed by 2 minus x raised by 4 over 6 plus so on. So in shortened form, it is written this way, right? Now in the last lecture, we have mentioned both sequences and series, right? Let me refresh your memory about the last lecture. 2, 4, 8, 16, 32, so on, 1, 2 over 3, 4 over 9, 8 over 27, 16 over 81. Similarly, AR square, AR cube. This list is list of sequences which we discussed in the last lecture. 2, 4, 8, 16, 32, then 1, 2 over 3, 4 over 9, 8 over 27, 16 over 81, or this general form. These are geometric progressions. So they are sequences, right? There's a list of sequences. So what is a sequence? A sequence is simply a set of quantities one for each n, a set of quantities one for each n. Then a series is an indicated sum of such quantities, right? A series is an indicated sum of such quantities as for example, I've already discussed it. 2 over 3 plus 4 over 9 plus 8 over 27 plus so on. So this or this general form A plus AR plus AR square plus so on plus A R raised by n minus 1 plus so on. So these are series, right? So the indicated sum of such quantities is a series, as this is series, this is series, right? So this was about the notation and the definitions. Now we will do an example. So let me write the example. The example goes like this. Find the limit as n tends to infinity of the sequence to n minus 1 raised by 4 plus square root 1 plus 9 n raised by 8 over 1 minus n cube minus 7 n raised to 4. So this is our example. So example goes like this: find the limit as n tends to infinity of the sequence. So we are given a sequence written in general form to n minus 1 raised to 4 plus square root of 1 plus 9 times n raised to 8 whole divided by 1 minus n cube minus 7n raised to 4. So we have to find the limit of this sequence as n tends to infinity. So what we do, we divide numerator and denominator by n raised to 4 and take the limit. Take the limit as n tends to infinity. When we do this, what will happen? Then all terms go to 0 except this term, 2 raised to 4 plus square root of 9 whole divided by minus 7, which is minus 19 by 7. Let me tell you, we simplify this sequence by dividing the denominator and numerator by n raised to 4 and take the limit as n tending to infinity. But we see all terms in this sequence go to 0 except 2 raised to 4 plus square root of 9 or minus 7, which is minus 19 by 7. So this minus 19 by 7 is the limit of this sequence as n tends to infinity, right? You do it, divide it yourself by n raised to 4 in the denominator and numerator, then take the limit and convince yourself. So check the calculation and convince yourself at home. So this is all for today. Let me summarize. So we connected this lecture to last lecture. In the last lecture, we gave the idea of geometric series and we discussed infinite series in general, and geometric series was used to understand ideas related to infinite series. Now in this lecture we said there are other infinite series besides geometric series, and we gave examples 1, 2 and 3. Then we defined infinite series in general. I said it is expression of this form where these an's, one for each positive integer n, are numbers or functions given by some formula. Then we said if there is doubt about how the terms are formed, we write a general or nth term in a series as in 5 and 6, right? Then we discussed how we write the series in shorter form using this summation symbol, and we give examples of writing them, 7 and 8. Then we define sequence. Sequence is simply a set of quantities, one for each n. So this list is list of sequences. Then when we add series, these quantities, we form a series as this is series and this is series. Then we discuss this example about the limit of this sequence as n tends to infinity. So this all for today. Don't forget to like, share, and subscribe my channel. And you comment in the comment box. Thank you. God bless you. Assalamu alaikum.